All right, in our last video, we talked about chemical reactions, and we said we need to be very careful when we're doing chemical reactions to ensure that the reaction is balanced. So we need those reaction coefficient whole numbers to go before each reactant and between or in front of any necessary products to ensure that atoms aren't created or destroyed. We also want to include the states just to be really thorough. But today what we're going to do is we're going to look at all the different types of chemical reactions. So specifically, we can branch them into redox reactions or non-redox reactions. And today, we're going to focus primarily on these redox reactions. So what in the heck is a redox reaction? Well, let's define it. So a redox reaction is a specific type of chemical reactions where electrons are being moved. So let's write this down. So it involves a transfer of electrons to or from, because there's going to be a receiver and a giver, an atom, molecule, or ion. All right. In your textbook, it talks a little bit about how redox reactions can involve moving oxygens and hydrogens around. I really hate that definition because it's not universally true. However, all redox reactions involve transfer of electrons. So that's the key point in a redox reaction. So let's further define this. Redox is actually made up of two different components. We've got reduction first, and then we've got oxidation second. That's why we got up with what got the name redox. So let's define reduction. That's the first half of what redox means. A reduction means that an atom gains electrons in a chemical reaction. All right, versus oxidation. Oxidation is essentially the opposite. An atom loses electrons in a chemical reaction. All right, and students always get this kind of mixed up in their head. So I'll show you a mnemonic that's pretty popular with our bio faculty. And this is Leo the lion goes grr. And you might be wondering, okay, what the heck does this mean? So what this means right here is losing electrons equals oxidized. So that's LEO, right? Versus GR, this is gain electrons equals reduced. There's also another one that's similar to this called oil rig. So oxidation is loss, reduction is gain, whichever one you want to use. I just use this as a mnemonic to remember. But like I said, I prefer this definition about transfer of electrons. Try not to get stuck on the hydrogen-oxygen definitions. They're really limited in their use, and in my opinion, they shouldn't even be in our textbook. I don't know why they're there. All right. So in order to determine if electrons are lost or gained, we must compare something called oxidation numbers or oxidation states for individual atoms. So let's go ahead and figure out how to do that. So I'll just write this down, assigning oxidation number. I'm just going to call this ON. Which is essentially the same thing as oxidation state. So I'll use that interchangeably, oxidation number, oxidation state. So let's just make a note here. So this is the same as oxidation state. All right, the rules for this are really straightforward. I know it can seem a little overwhelming when you're learning them at first, but the more you practice it, the easier it is. So rule number 1 is that elemental forms always have an oxidation number equal to 0. So let's take a look at some examples of this. So let's say I have a reactant and it's just aluminum metal, right? So elemental symbol for aluminum is Al. Well, that means that the oxidation number for aluminum is just going to be 0, right? Because it's elemental, it's by itself, it's just aluminum. All right, let's take a look at another one. What about O2? Well, some people will look at this and they'll say, well, it's 2 oxygen atoms. But remember, it's still elemental. It's just made up of oxygen atoms. So this is the natural state of oxygen atoms in our world. So the oxidation number is going to be 0. Same thing with something like bromine. If we do Br2, this, because it's just made up of bromine atoms, would still be an oxidation number of 0. Same thing with something like gold. If we think about gold, Au, this would be by itself, so we just say 0. So if you ever see an element, even if you've got some sort of subscript after it, but that element is only one type of element, remember the oxidation number is going to be 0. All right, so that's rule number 1. Rule number 2 is to treat all atoms as ions, even if they aren't. Okay, you might be wondering, why are we doing this? Well, the ionic charge equals the oxidation number if you do this. All right, so let's take some examples here. So let's say that we've got sodium chloride. This is nice because sodium chloride is just made up of ions, right? So if we break this apart into 2 pieces, we'd say, well, this is made up of sodium cations, which are Na+, and chloride anions. So what we could do is we could say, well, because sodium is a +1 cation, we would just say the oxidation number is going to be +1 in this case. So not too bad. And then chlorine over here, we'd say, well, this is -1. So the oxidation number for chlorine would be -1. All right, let's do another one though. Let's do a different one. Let's think about H2O. Well, if we think about this and we look on the periodic table where hydrogen is, we'd say, well, hydrogen, if we were to pretend like it's an ion, would it be more likely to be a cation, meaning would it lose electrons, or would it be more likely to be an anion and gain electrons? Well, in this case, hydrogen is far more likely to lose an electron because it's in group 1A, right? So it could lose 1 electron pretty easily. And we'll talk more about this later. There's some tips and tricks. But hydrogen would be viewed as a positive charge. So each of these hydrogen atoms would be +1 for the oxidation number. Versus oxygen. Oxygen is in group 6A, which means it really wants to gain 2 electrons, right? So oxygen as an anion would really like to be 2 negative, right? So if we do this, it would be -2 for the oxidation number, which kind of makes sense because if you think about -2, it's going to balance out with the 2 positive ones for each of the oxygens. So hydrogen, let's make a note here, is almost always +1. So that's a common trick you can use. Some students get confused by that. All right, let's try maybe one more of these. Let's try doing something like CH4. Okay, so this is CH4, that's methane. It's natural gas. It's what a lot of us use to heat our home. This is a covalent compound just like water, but we're going to pretend like it's ionic to find the oxidation number. All right, so this gets trickier, right? We've got hydrogens. And so we said hydrogen is always going to be +1, right? So over here, we could go ahead and we could say for this one, this is going to be +1, and we've got each. But carbon is tricky, right? If we look at carbon is in group 4A. So there's kind of this question, what ion would carbon form? And the reality is, well, it depends, right? If we think about this, if we've got 4 hydrogens times +1 each, that means that the net oxidation number for the hydrogens is going to be +4. Well, that gives us a big clue about the carbon, right? Because we want all of these to cancel out. So if we go ahead and look at the carbon, that indicates that carbon, in this case, would be 4+. And we know this simply based off of looking at, 4 negative. And we know this based on looking at the hydrogens. We said that the charges essentially have to cancel out. So this would be -4 as the oxidation number. All right, so let's just make a little note here. So we can infer this must be -4 to cancel. And I'm just going to go ahead and move this over here so it's out of the way. And that brings me to my next point. All right, so in number 2, I said, try to treat every single atom as an ion, even if they aren't. And so in this case, we said that water and methane are covalent compounds, but we treated every single atom as ionic to find the charge. All right, number 3 says that neutral molecules should have a sum of oxidation numbers, and I'm just going to call oxidation numbers ONs, equal to 0. So the example we gave up above was methane, right? So with methane, we didn't know the charge of carbon. We had to infer the charge of carbon by looking at the charges of everything else that we were positive with. All right, but we were able to do that by knowing that everything should cancel out. But this only works for neutral molecules. All right, let's take a look at polyatomic ions. So for polyatomic ions, should have a sum of oxidation numbers equal to their charge. All right, so let's take a look at an example situation for this, right? So let's say we've got something like MnO4 minus, right? This one's a little bit tricky, but we can look at oxygen and we can say oxygen is in group 6A. So this means the oxygen atoms like to be -2, okay? So we'd say 2 negative, and we've got 4 of them, so I'm just going to go ahead and write out 4 of these oxygen atoms in their preferred ionic state, which is 2 negative, right? We said that group 6A elements really just want to gain 2 electrons to get their octet. They don't want to lose all 6. It's easier to gain 2 than it is to lose 6. However, manganese is very different, right? Manganese is right smack in the middle of the periodic table. That's with the transition elements, and it's really hard to know the charge of anything in the middle of the periodic table. If you're on the far ends, it's really easy, but if you're in the middle, it's really hard. So let's go ahead and just write down a question mark here. Well, Let's try to turn this into a little bit of a math problem for us. So I'm just going to say, let's turn this into an x variable. Okay, and we know over here that this is going to be the sum of all the oxidation numbers. Okay, well, let's do the math. We know that the x variable, meaning this value right here, plus all of our other components, which in this case is going to be -8, right? That's where all of these go into play, are going to be equal to -1, the sum of all of our oxidation numbers. Well, let's try to solve for x now. Well, that's not too bad. We're just going to add 8 to both sides. So we'd say that x must be +7, right? Which tells us that we're dealing with manganese that has an oxidation state of 7+. So it's a little bit weird that way. Like I said, oxidation numbers for transition metals can be a little bit tricky. So let's go and kind of recap common charges. All right, so I'm just going to paste this table in. It's actually from a different textbook, but it gets the idea across pretty easily. And let's just paste this in. So we've got this periodic table, and I'll just make a few notes. So over here in group 1A, so group 1A is always going to be +1, right? And that's pretty easy to remember. And then over here, we'd say group 2A is going to be +2. So that's pretty easy to remember too. And then over here, group 7A is going to be, -1, right? It's easier to gain 1 electron if you're in that group than it is to gain all or lose all 7. And then over here, we've got group 6A is -2. However, like I said, basically everything in the middle from here to here, we have to infer. So we'll just say have to infer. It's a little bit less reliable. But like I said, if you follow the rules kind of as outlined for number 3, you should be able to use this inference to determine the oxidation number for any questionable elements that reside within this middle portion of your periodic table. All right, this video is a little long, so I'm going to stop here, and then when we come back, we're going to do a lot more practice.